तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Welcome back to the lecture series in computer graphics. We are towards the end of the lecture series, and today we will talk about advanced concepts in computer graphics. Basically, it will be an introduction to the concepts, techniques and methods used in latest computer graphics literature, which could be a stepping stone to concepts such as virtual reality, visual realism and things like that. Okay, so, let us look back into the slide when we talk about advanced concepts in computer graphics here, and we are going to discuss in very brief concepts such as anti-aliasing, texture bump mapping, animation, soft object modeling, and we will conclude with visual realism. What is visual realism? Let us start with anti-aliasing. What is anti-aliasing? Well, you remember the concept of aliasing with lines, points, circles and any other figures which we draw. So, we need to remove the effect of the aliasing. The other terms which were used in aliasing were jaggies or staircases. So, if you look at aliasing, it occurs when signals are sampled too infrequently, that is, we have coarse sampling done, giving the illusion of a lower frequency signal. Well, the concept of aliasing is a very common concept used in signal processing, and we will try to see, without getting into deep of the concepts of sampling theorem and aliasing effects in the signal frequency domain, how does it occur in computer graphics as well. So, that is aliasing for you, and to just give you a brief example, a simple example for that matter, if this is an analog continuous function on the left hand side for you, and that is a sampling function. A sampling function is also talked of as a comb function. Basically, what you do, you overlap the sampling function on the continuous function and sample it at regular intervals of time. So, wherever you get a non-zero value of the sampling function, multiply it with the continuous function value at that point in time, and that is where you get the discrete samples, which are the vertical lines here. The dashed line here shows the continuous function which is analog or continuous, and then you have the discrete samples. This is very common in signal processing, and that is what is used in computer graphics also when you have discrete samples as pixels spread over an image, but in this case we are taking a one dimensional equivalent or an example in 1D to understand the concept clearly. So, I repeat again, sampling function multiplied with the continuous function gives you the discrete samples at regular intervals of time, and if you take this, you can take any reconstruction kernel. I have taken a very shallow ramp function, which if you convolve with this function, you will get a reconstructed signal like this. So, this is an approximated reconstructed signal of the continuous function which you see here, and you can almost see the effect of discontinuity, the coarseness in the signal represented in the discrete digital domain corresponding to the analog 1D analog continuous domain here. What are the drawbacks which are caused by aliasing? Let us take an example in 2D now. The left hand side is an original function, let us say a 2-dimensional example, you have discrete set of pixels, and if you have say the part which should have been in colored and the background being dark here, then when you try to render it using a concept such as which says that if the majority part of the pixel or 50% of the pixel is covered by this area, then I will shade it completely, otherwise not, then you have this rendering effect which is causing the aliasing effect after rendering. You can see the staircase effect very clearly in the discretized domain. This is a continuous curve, a continuous 2-dimensional function covering a finite 2D area. Okay. The things could be very severe in situations like this. Let us say when you have the original signal here, this example we have obtained from a particular website, but you can create this very easily. As you can see here, that there are various types of two-dimensional shapes, a rectangle, triangles here, small and big, and again a rectangle on the top. And when you use concepts such as area coverage in trying to fill up this area, you will end up with you will actually obtain a rendered image which looks very different from the original image. So, that caused jagged profiles or loss of detail. These are the problems with aliasing. It caused disintegration in textures as well. This is a three-dimensional texture gradient. As you can see there, of course, there is an aliasing effect as you move along the edge of the tiles, but more than that, as you move away towards the direction of what is called the foreshortening. This is a perspective projection of a planar surface painted with texture, and as you can see far away, the textiles do not line up very prominently as the tiles which are closer to the viewer. So, what are the techniques to reduce this concept of aliasing, which deals with anti-aliasing? Anti-aliasing techniques, the one which is not commonly used, but helps quite a lot, is trying to increase the resolution of the system. As for example, left hand side, if you see, let us assume that your Bressenham's line algorithm has created this set of pixels to draw a line from a point P1 here on the left bottom to a point P2 on the top right, and these are the pixels which you get using the Bressenham's algorithm or the round function. Let us say that is a digital differential analyzer DDA algorithm, then you can see the jagged nature of the staircasing effect. You can probably increase the resolution to double, and you will get a set of pixels like this where the line appears much more smoother. You can keep on increasing the resolution of the screen, and the aliasing effect will be less and less, but you know that you cannot go beyond a point. Not only that, increasing the resolution of the display device from one level to another involves a lot of cost in terms of money as well as in bandwidth. So, there are monetary issues, there are issues in terms of bandwidth. When we talked about display devices, if you remember, there is a lot of bandwidth necessary between the video controller and the output display. So, it involves more memory cost, bandwidth, and scan conversion time required. As you need to obtain the set of pixels from left to right, the amount of time required to obtain the set of pixels is double or more than the amount of time required on the left hand side. So, this is not a good solution, the increasing resolution. So, what do you do? The next technique is called area sampling. In area sampling, what you basically do is you try to set the intensity of the pixel value which you are going to shade and obtain using Bressenham's algorithm proportional to the amount of area covered. We will see with an example what is this, setting the intensity proportional to the amount of area covered. Well, the intensity decreases as the distance between the pixel and the edge increases. That is also one way of trying to reduce the aliasing effect. We will see with an example what do you mean by the intensity decreasing as the distance between the pixel and the edge increasing. Well, you have a concept such as unweighted area sampling, but which is where we will say that the equal areas contribute equal intensity regardless of the distance between the pixel center and the area, only total amount of overlap area matters. Let us understand the concept of unweighted area sampling with the help of an example. If you see here this example, we are talking of a line which starts from the pixel here to the point there, and as you can see that the amount of area covered by this rectangular line, which we assume to be about 1 pixel wide, the amount of the area covered by this rectangular strip of the line, because the line is assumed to be of finite width now in computer graphics, and whatever area it covers over a pixel, we calculate that particular area coverage and shade it with that particular intensity. Well, if the pixel is almost entirely within this rectangle, let us take this pixel or even this one now, you can see some of these pixels have been painted absolutely dark, assuming the background white. It could be the reverse, you can have a background dark, foreground white, whatever may be the case. It is a question of how much of the pixel's area is covered by this rectangle. If the entire pixel or almost the whole part is covered, you use the full intensity. If the area coverage is less, okay, you reduce, and if it is still further less, you reduce and make it close to the foreground. So, as you can close to the background, excuse me. So, as you can see here that the pixels which are to the left and the right have lesser intensity compared to those which are in the center, and the intensity is hence proportional to the area covered. So, this is a concept which we just read again of the unweighted area sampling, where we say that equal areas contribute to equal intensity regardless of distance between the pixels center and the area, only the total amount of overlapped area matters. Since the total amount of area overlapped matters only regardless of distance, hence it is called an unweighted area sampling. There exists a weighted area sampling which we will understand now. This is the concept of weighted area sampling as given on the top of the screen. Remember, the one at the bottom is an example of unweighted area sampling, because it is written clearly that the intensity proportional is proportional to the area covered. Okay, intensity is proportional to the area covered. Well, what is weighted area sampling? We will say here that equal areas contribute unequally, equal areas in terms of overlap. A smaller area closer to the pixel center has a greater influence than does one at a greater distance. So, not only we have to calculate in case of weighted area sampling the amount of area covered by the rectangle of over a pixel, we also have to do, what we have to do is find out how much is the distance of a center of a pixel from the center of the line. So, there are two factors which one has to take into account in terms of trying to compute weighted area sampling based anti-aliasing. You have to find out how much is the area coverage, that you can easily calculate in terms of the rectangular finite width line with a finite width is a rectangular strip, how much that covers a particular pixel. If it is full, go for the full intensity. If it is half, use half of the intensity. If it is nil or approximately close to 0, use a negligible amount of intensity to shade that pixel. That takes care of the unweighted area sampling, where the area overlap only matters. In case of weighted area sampling, you have to of course first calculate the area coverage, number one. Number two, what you have to do is you have to basically find out what is the distance of a pixel from the center of the line. Okay, so use that, a 1 by d square term or 1 by d multiplied by the area coverage. So, there are two factors. So, if there are two pixels with similar area coverage, with same amount of distance, the intensity put to that pixel will be the same. But however, if one of the pixels is closer, to the center of the line, that will have more intensity than the one which is further away from the center of the line, and that is the concept of weighted area sampling. We will wind up this concept with this statement. We will read again, where we will say that equal areas contribute unequally. Mind you, it was contributing equally in the case of unweighted area sampling, but in the case of weighted area sampling, equal areas contribute unequally. A smaller area closer to the pixel center has a greater influence than does one at a greater distance. Let us look at other concepts of anti-aliasing, which is based on point sampling, where in this case we select one point for each pixel, evaluate the original signal at this point and assign its value to the pixel. What does this mean? That it has certain drawbacks. We will read this drawback and see the example. The projected vertices of a polygon, let us consider the vertices of a polygon, are not constrained to lie on a square grid. Let us see this particular example. As you can see, the problems in point aliasing here, what we are basically checking here is whether the pixel is falling within an area. If it is falling within an area, you use the color of that particular area to shade the pixel. But if the object is so shallow, so small that it lies within a resolution grid, remember, let us assume that the background is the analog world, the foreground is this grid of pixels which we have overlapped on this analog area, and we are sampling the continuous analog world using a 2D array of points. Okay, you remember the cone function we talked about in aliasing, which was an array of 1D vertical strips. So, you can visualize that as if you have a 2D array of thorns which you are putting on the analog world, and you are sampling each of the using each of those tip of the thorns, the continuous analog world. Okay, so that is what you have to imagine. A bottom is an analog world, continuous domain, a discrete domain on the top, and you are using a set of points to sample each particular point x and y in the continuous domain. So, if this is the case, there is absolutely no problem maybe when areas cover a pixel, but look at this particular rectangle or the triangle here, none of the vertices, in fact, none of the vertices may fall actually on the intersection point or a grid point, and the entire area may actually fall outside. area may fall outside a grid point, and these are the problems which could be associated with the point sampling, where you will not get the any grid pixel will not be illuminated due to the presence of this triangle. So, that is the problem with point sampling, where we will see that the projected vertices are not constrained to lie on a square grid. So, because of the signal's values at a finite set of points are sampled, the important features of the signal may be missed. We have already seen that with an example, and the approach of taking more than one sample for each pixel and combining them is known as a concept of super sampling. So, that is a method by which we use to counter the aliasing problem in point sampling. The super sampling, it is similar to the concept of super resolution in image processing, where in super sampling we take more than one sample for each pixel and then combine them to obtain sample points. Okay. Super sampling corresponds to reconstructed signal and resampling of the reconstructed signal. I repeat, super sampling corresponds to reconstructing the signal and resampling again the reconstructed signals. Okay. Continuing with another method of anti-aliasing, which is called filtering. This is done by removing high frequency components from the original signal. The new signal can be reconstructed properly from a finite number of samples. Well, we did say that aliasing corresponds to as if some coarse sampling. Now, coarse sampling, whenever it is done without an effect of smoothing, it typically results in this Jaggis or aliasing effect or the staircasing effect, and there will be high frequency components present in the signal, which is equivalent to saying that there are some ripples or staircasing effect, which is the effect of aliasing we observe in computer graphics, and the similar concept is also exists in concepts of digital signal processing. Okay. So, we have to remove these high frequency components by method of filtering. Let us see this example of the original image. Okay. As you can see, textures which are very close, the texture of the tiles which are very close to the viewer or closer to you, you have almost no effect of aliasing. But as you go further beyond, in this part of the of this planar inclined surface of the texture, which is inclined here, as you can see through the beaker or within the beaker, there is a strong effect of aliasing. You must come close to the screen to observe the effect of aliasing here as well as there as well as here. I cannot enlarge this image much larger because I have to squeeze in the effect of anti-aliasing using filtering here. So, please come to the screen and observe here the effect of aliasing at this region, even at this as well as in this region. There is barely an effect of aliasing at this location. Let us try to find out what do you mean by high frequency components here. Well, if you pass it through a high frequency filter, basically it suppresses all the low frequency components in terms of brightness values, where whatever bright is the brightness contrast within the tiles are removed, and in fact all the aliasing effect comes here. So, if you logically, in terms of logical, I should not algebraically subtract this high filtering signal from the original image, basically pass it through a low pass filter. A typical example of low pass filtering is to use a Gaussian function. You can see that you get this image. Yes, it appears blurred compared to the original image, all right, but if you can carefully see here, again I would request you to come close and observe these areas. One area here very light, you can see it is a blurring effect, but the effect of aliasing has disappeared. There was a strong effect of aliasing here which has almost disappeared in these ranges here. So, this is one way with the help of filtering, basically you need to use a low pass filtering to avoid the concept of aliasing. Okay. So, that concludes the discussion of anti-aliasing. We have just time to discuss a few of these techniques, and we have to move forward and discuss about other concepts of advances in computer graphics. Let us look at the next topic, which is texture bump mapping. Okay. Texture bump mapping. What is texture bump mapping? Well, it is like a texture mapping where you map a texture onto a surface, but it is a technique which adds more realism to synthetic images without adding a lot of geometry. Texture mapping adds realism by attaching images to geometric surfaces, whereas bump mapping adds per pixel surface relief shading, increasing the apparent complexity of the surface. We will see what you mean by this later on as we go along. Bump mapping adds per pixel surface relief shading, increasing the apparent complexity of the surface. Bump mapping is done for surfaces that should have a pattern roughness. Examples include surface of oranges, surfaces of strawberries, stucco, wood, etc. Wood means you can probably visualize the trunk of a tree. Stucco is the textured 3-dimensional ripple texture surface which is done for indoor decorations or even outdoor decorations for that matter. So, any rough type of surface which you can visualize ripples existing on a surface, that sort of relief shading is provided with the help of bump mapping. You can almost visualize the scenario when you have a road with lots of bumps in front of you. Okay, that is of course very regular and periodic in the sense that there is absolutely no randomness. You can visualize a series of bumps on a road by simple sinusoidal variations, but there is lot of randomness when we talk of texture, not like a random noise. Well, there are methods which can do that, but we are talking of some sort of randomness in the shading effect when you talk of texture bump mapping. So, these are examples of surfaces: oranges, strawberries, stucco and wood, where the bump mapping is done for surfaces that should have, or you want to provide a patterned roughness on the surface. An intuitive representation of surface bumpiness is found by a 2D height field array. So, you are talking of a 2D height field array called a bump map. So, if you have a planar surface z equal to constant instead of z equal to fxy, and then you assume that you put another layer on top of it, where the z function when the second layer is sitting on a planar smooth surface, and that provides the bumpiness or the roughness. That could be a random sort of a variation to provide the texture, but it basically implements the bump map for you. Okay. That z equal to function of xy could be a small randomly varying function. Okay. It should not be too random like a noise, but there should be some randomness in terms of creating this bumpiness on the surface. So, we need a bump map which is also called the 2D height field array to create the surface bumpiness. Well, the bump map is defined by the scalar difference f of uv. Well, although you have two parameters u and v and it should be a scalar, but at any point u and v there is a scalar difference f between the flat surface puv and the desired bumpy surface p prime uv along the normal n at each point u comma v. So, this is the one which is varying. The desired bumpy surface creates p prime, which is a random variation at of u comma v along the surface normal, and that sits on the flat surface puv and creates your fuv, that is the bump map, final bump map. So, you talk of a layer puv, another p prime sitting on p, and that creates your f, the bump map. We will see examples as we go along, but let us read a few more concepts. A bump map is hence an array of values that represent an object's height variations on a small scale. I repeat again, a bump map is an array of values that represent an object's height variations on a small scale. A custom renderer is used to map these height values into changes in the local surface normal. Well, we do not have time to go through these equations, but I would like you to refer to Fong's shading models, where if you remember we had taken the normals at the vertices and used that to interpolate along the edge, and from that edge we use scanline method to compute the normals at each surface and then use shading. So, a concept similar to that could be used for texture bump mapping, where you recompute the surface normals at each vertex and then use relief shading on top of that to create the effect of texture bump map. So, a custom renderer is used to map these height values into changes in local surface normal, and then these perturbed normals are combined with the surface normal, and the results are used to evaluate the lighting equation at each pixel. So, just mentioning this, these perturbed normals, remember, are obtained when the normal height values are changed and that causes a change in the local surface normal, and then these perturbed normals are combined with the surface normal, and the results are used to evaluate the lighting equation at each pixel. Let us look at a few simple examples. This is the one which is an example of a texture bump map. This also has been obtained from an example created by one of the institute websites, and that is an example, as you can see, the surface roughness and the brightness pattern. Well, texture bump map is one of the techniques which is used to create this nice visual effects, but there are other visual effects possible. I will probably list them towards the end of this lecture today, and a few of them will also learn. Along with aliasing, you need to provide texture mapping and a few other methods to really create realistic pictures. Let us look, before we move on to another concept, let us look at a very realistic picture as to what we are trying to make. If you look at this picture, again simulated, this is courtesy from this particular website. You can try this. There should be a gallery of other objects as well, realsoft.fi, and as you can see, this is a realistic realistic scene rendered using various types of concepts. Well, you use NURBS, which are non-uniform rational B-splines. Once read about this, we talked about B-splines in our lecture, and slightly advanced equations will talk about NURBS, which are used in all sorts of VTKs and softwares, advanced toolboxes like Maya. RealSoft has its own engine which will use NURBS, so that's very common for creating polygons, meshes, various types of complex structures, even it could be a dinosaur, another complicated structure. So people use NURBS. So NURBS have been used. Along with that, image maps, bump maps, texture map, procedural noise, which is a very interesting concept. There are concepts of procedural noise which deals with concepts such as Perlin noise, three-dimensional noise integrated with it's not truly random in the, like a noise, but it is not rhythmic like a sinusoid or not periodic like a sinusoid. So it's somewhere in between, and there are very interesting concepts which if you go through a course of advances in computer graphics or virtual reality or visual realism, you must study concepts, various other concepts including procedural noise. Well, and depth of field. Well, this depth of field we have studied when we talked about shading. This is an effect where the distance object should appear lighter than objects which are closer to you. That is the effect of atmospheric attenuation, was an example which we studied for depth of field. So you can see that I have used this website where among the different galleries of objects we have the surface bump map on the apple, we have eggs, we have a vase which has two layers, one layer of blue, another is a shiny layer on top of that, and of course another texture procedural noise is used for shading this particular vase itself. So that's a nice example which appears almost close to reality. This is a very nice example I thought, which you should see which one can try to simulate. So and there are various concepts, some of them which we study, some of them which we don't study in this basic introduction to computer graphics last lecture, almost towards the end of the lecture, about different advance in computer graphics. Some of these basic will just introduce the concepts and terminologies of advances in computer graphics, but may not be able to cover all topics. We will look at the next topic, which should be interest to many, basically especially for video game designers. Here is the concept of an animation. What is animation? Something which moves. What are applications of animation? Well, there are special effects and movies in TVs which needs animation, video games need animation, virtual reality, everything in front of us moves. So when you want to create reality in a virtual domain, things must move, and when things have to move, they must move efficiently in a smooth manner, not in a jerky manner, which will create an aliasing effect also in motion. So virtual reality, then simulation, training, and in military, medical applications, robotics and animatronics. Well, that's an example of robotics and movements of robots, or electronics mixed with animation, I should say, is animatronics. Visualization, okay, and communication as well. What is animation? It's a technique in which the illusion of the movement is created by photographing a series of individual drawings in successive frames of films. Typical example is a cartoon production. Okay, these are various examples. You can obtain some of these on your web. Of course, these are static pictures, but these are some examples of animations created. I have only got a static picture in some of these. Of course, this is an example which is obtained also from the web page which of the institute which works on the movies of Star Wars, okay, and these are of course are cartoon movies. Well, the animation pipeline can be visualized as a stage of blocks like this, a flow chart. We talk of a 3D modeling, then we talk of an articulation of the models which have to move, the specify the motion in terms of motion specification, simulate the motion, shade individual pixels and regions on polygons, talk about light source, render them, and do some post processing to eliminate the effect of aliasing, jaggies, and jitters if they are present in this motion. So these are the examples of animation. Okay. Now there are of course various categories of animations possible. We will just touch upon a few of them. There is a difference between what we call the 2D and 3D animation. Well, we don't have an example, but I will try to illustrate that with a static picture, the difference between animation characters in 2D and 3D. Well, you can see here that this is an example of a 2D animation character, because this can only move in 2 dimension there is 2-dimensional structure, but there is 3D information here. This person can not only turn around, but can move up and front in 3D and can revolve and rotate around. This character is mainly meant for 2-dimensional animation. This in the right hand side is meant for, this is again a static picture meant for 3D animation. Well, when you talk of types of computer animation, there are basically 3 types: a keyframe animation, procedural, and motion captured animation. We will read what is keyframe animation for us. Well, we define characters poses at different time steps called keyframes. We will see what are these, where we define character poses at different time steps called keyframes and interpolate variables describing the keyframes to determine pose of characters in between. This in betweening is a very nice concept with keyframes, which we will see here. Let us look at trying to create different poses of a particular character. I have taken this example of a table lamp. This is the first pose. The second pose is where it moves a little bit up. This is the third pose where it is spring up. So it's a dynamic, I will say it's a dynamic table lamp, and then it moves here and it's falling down. Okay, it's coming back to its original position. These are, so it may move in this arc. It's possible that you might specify that it may move in this arc, but it could be in the same location where it could spring up and down at the same point without moving from left to right as given in this curved path here. That is possible, but also in the same position if you see that it could jump up and down, and these are the 6 different poses at the same location. Okay, so that is possible, but of course it is better to provide a lively animation by moving the entire structure as well at different time instances as when the shape of the structure changes. So, what is keyframes and in between? Let us say there is a big amount of discontinuity here between, and I select 2 keyframes here. This is keyframe number 1, keyframe number 2, and I am interested to create another frame, simulate another frame in between. So, this is a concept of in betweening which could create animation frame like this in between. Well, I must admit here you must carefully observe that if you only use these 2 frames, let us go back, if you use only these 2 frames to create and interpolate in between, you might get the same frame back. You will not get the one in red which I just shown. What you must do is try to interpolate back from the previous frames and also the next frame, and then only it is possible for you to get a frame like this in between. So, you need a little bit of mathematical skills, not simple interpolation, to create an in between frame from keyframes. Let us look at the different topics of interpolation. In betweening, concepts of linear interpolation, well, it is not a very sophisticated method where, let us say if you are talking of an analog trajectory like this, a modulated sync curve or a damped sinusoid, modulated, I am sorry, this is not modulated, this is rectified sinusoid you can say, and if you do an interpolation in between, you will get frames which are not accurate, as you can see here. So, typical linear interpolation is not good. What is done is a cubic spline interpolation. As you can see here, these could be a set of keyframes which I could use to create any frame in between. Now, I will use a set of all these 5 frames and find out the paths of this set of points within this structure from one point to another. Remember, these keyframes does not show the movement of patterns as like in the previous keyframes of the animation I showed in the previous slide, all right, but I am just showing you the position of the structures at what time frame. T is on the right hand side axis. Okay, vertical axis typically shows the curve which you will fit across the time frames, and you can use this cubic spline interpolation to come up with a frame in between at any instant of time, but you must use all of them. If you use just 2 of these, you will get a linear interpolation and you will may not get the actual change of the animation character. This is another example of spline interpolation which gives you a very good idea. I hope you can see the lines in between. So, you take a keyframe k and a time keyframe k plus 1, and what you do basically is use these use a set of keyframes k, maybe k minus 1 as well, k plus 1, k plus 2 to fit a spline and get a frame in between. So, that these are examples of what is called in betweening between frames. Very rarely, if there is a smooth amount of variation, very less amount of movement, for simplicity, for fast implementation, you can use linear interpolation, but typically it is better to use cubic spline or some sort of spline interpolation to obtain keyframe animation. Okay. Okay, keyframe. Let us move to the next part of animation, which is procedural animation. We will go through the key points in the procedural animation. Most of the work is done by a computer. Object positions and shapes are controlled by particles, flocking and crowd systems. Typical examples are cloth, fire, smoke and water simulations. These are certain examples of static picture about smokes simulation, okay, where the concept of particle systems are used for smoke, flocking and crowd systems, and soft object modeling is done for human and cloth animation. You can make them move only if the modeling is very correct. Okay. There are of course these advanced topics which I am not covering about particle, flocking and crowd system to generate cloth, fire, smoke and even water simulations. What is motion captured animation? This will be of interest to some people. Most of the work is done by the human actor, and human joint angles are taken from a live model via sensors on a motion captured suit. So, this is an example. People who are used to outdoor games such as baseball, cricket, etc., are this concept should not be new to you, because we know in the past that there are these laboratories which not only try to simulate, but experiment and also try to obtain to correct the motions and the pose of certain sports persons. If some say, if you take the example of cricket, well, the bowling action of several bowlers from within the country and abroad have been tested using simulation labs in Australia, which basically does the following, where they will put at the various joints of the human body different light emitting devices, and there will be sensors which will capture this motion and try to find out and simulate this interactivity, and then you can put it on a robot to create this animatronics which we talked about, and you can create the robot movement as smooth and as real like a human being, provided you know the motion parameters, the motion path of the way humans move when they are either walking or playing a certain game or doing some other activity. So, this is a motion captured animation, where he captured the path and the parameters of a human being when a certain person moves or in a certain activity, and capture the motion of all the parts of the human body, and then put those parameters inside the simulation of the character at the respective points and move it in a similar path. So, that is the motion captured animation. So, we have seen keyframe animation, procedural one, and examples of motion captured animation as well. We move to the next topic, which is also of interest, called soft modeling of objects. What is soft modeling of objects, or what is the need of soft modeling? Well, various deformable parts such as cords, leather products and sheet metals are handled and manipulated in a lot of manufacturing processes. You need to simulate them. So, modeling of deformable objects is thus required, so that the shape of the soft objects can be analyzed and can be evaluated on a computer. We need to simulate them not only for creating movies, creating video games, but also it is necessary to give a simulation for a designer, for an engineer, for an evaluating team. You may need, not all objects which we deal with in the factory and real life are hard rigid objects. Some of them are soft. A typical example of it is a cloth, some fruits, the tennis ball is also a soft objects, but cloth here, muscle tissues which we have in our body are all examples of soft objects, and it is often necessary to model them as well to create a real effect. So, that is the need of soft modeling, where we talk of modeling of deformable structures or objects, and it is required so that the shape of the soft object can be analyzed and can be evaluated on a computer. What are the applications of soft modeling? Computer-aided design and computer drawing applications. We talk about these as a class of applications of soft modeling, where deformable models are used to create and edit complex curved surfaces and soft solids, I should say. Computer-aided apparel design, which is used to simulate fabric draping and folding. We already seen that example, one such example in the case of an animation, where we saw a structure of a human being and with a cloth draped on top of her. So, that was an example where you needed soft object modeling to simulate the apparel or the fabric. Okay. Image analysis, it is also used where you use to segment images and to fit curved surfaces to noisy image data. That is not the best example of computer graphics, but it is also used, and surgical simulation and training systems. So, that is another good example of soft modeling. Techniques for modeling deformable models. What are the techniques which are used? Well, there are lots of them. We will just go through a few of them, and we will take one example to study in detail with the time available to us. Non-physical models involve splines and patches. We talk about Bezier curves, double quadratic curves and B-splines, which are used to model non-physical models. Non-uniform rational B-splines. We talked of these nerves already when we saw that very highly realistic example after we talked about texture bump mapping. Nerves are very common, and also people use beta splines used to represent planar and 3D curves. Well, free-form deformation, FFD, where it is a general method for deforming objects that provide a high and powerful level of control. Free-form deformation is an example, is a concept which is a general method for deforming objects that provide a very high and powerful level of control. Continue with the discussion with physical models. Well, this is the most common example, which is used, called the mass spring models. What is done here? An object is modeled as a collection of point masses connected by springs in a lattice structure. I repeat, we will come with this example in a figure very soon. We are talking of an object which is modeled as a collection of point masses. So, each point structure will have a mass. It is a small, infinitesimally small object with a mass, and they are connected by springs in the form of a lattice structure. Let us see this example. And this is widely used in face animation as well as for modeling tissues, springs, and even let us say soft objects such as sponge structures, where these are the points which will have certain mass, and there are springs in between. All of them could be of the same value. This is the spring constant k, the mass m. All of these structures may have the same mass, or it may be different mass adhered to or stuck to each point. The spring constants could be different, or they may be same all over. So, this is typically a cubic structure, as you can see here, but you can form any structure, a 3D array of points, put mass on each of these points and springs connected, instead of a rigid structure where in the case of a wireframe, if you remember, there was just a line joining between two vertices, and it was very rigid under any transformation like rotation, translation, scale, except maybe shear. It was invariant, but you can apply a force on this soft object, this springs, mass spring structure, and what will happen? You can try to visualize what happens when you apply a force on a spring. You know the springs theory from the concepts of basic physics. Now, a set of springs put together, and you apply pressure. Some of these springs will contract, some of them might expand, and that will allow deformation of the structure. So, that is the concept which is used in the mass spring model here. So, I repeat, an object is modeled as a collection of point masses connected by springs in a lattice structure like this. Well, the spring forces are often linear, but nonlinear springs can be used to model tissues such as human skin that has inelastic behavior. I repeat, spring forces are often linear. We can have a spring constant k, and the equation could be linear, but we can have nonlinear springs as well, which can be used to model tissues of human, such as human skin, which has not elastic but inelastic behavior. So, that brings us to the conclusion of the soft object modeling. We will move on to the next concept based on the permissible time limits, which will bring reality into the picture. Okay, it is called image based rendering. Let us look at this example of image based rendering, or IBR as it is called. IBR, or image based rendering, refers to a class of rendering methods. It takes a series of images as input. So, it might be a video. Okay. So, often video based rendering and image based rendering are used interchangeably. If you use a single image or a couple of images, maybe at the most, you can talk of image based rendering, but if you talk of a sequence or series of images, you can say you are using a video based rendering as well. So, what does it do? It takes a series of images as input and uses them to form a new image from different camera locations. I think this concept of image based rendering people have seen in movies and even in sports. It is a concept such as, let us say you observe my face from the front. Now, you are observing with the camera which is being shooting this lecture. It is possible that there could be another camera on the right side of me which could also be taking this picture, that is also possible. Okay. What could happen? That means I am using two cameras, one on the front side, another on the side, and the side camera will capture my side view. Okay. It will capture my side view as I speak. This is an example of the camera if I had used a side camera with a side angle, and if you have two such cameras, it will take two views. Now, what is the problem which I am trying to solve here? With these two views, as I am speaking and talking to you from the front, and the side camera taking my side view, let us say, I would like to simulate a view of an image or a video of a camera. Imaginary does not exist, but I want to simulate that shots, okay, for a camera which exists at an arbitrary oblique angle, say at 45 degree with respect to my face. So, you will probably, I want to simulate the video of the speaker talking at a particular angle, as you can see me here. Okay, only you have the front and maybe the side view. So, that is an example of image based rendering trying to simulate views from a different camera locations. It could be at any arbitrary angle. Of course, all camera angles may not be possible. You need lots of camera views to really create different types of views. At least from two camera locations you can obviously simulate a third, and the third is the correct, you can also generate a fourth. So, that is a concept based on image based rendering. Okay. Of course, there are other applications of image based rendering where you try to provide a texture on a surface where the texture is brought from a realistic image. That is also an example of an image based rendering, and it gives you a good simulation of reality, because you are using real images, not artificial ones, real images, shadings, shadows, intensities obtained from real images to shade it on a picture which is a simulation. That simulation model itself could be a computer graphics simulation, all right, but you are not going to calculate the intensities, brightness and reflection patterns on any surface, whether it is a human being speaking or any other event, sports or whatever it is happening. You are using images and pixels and intensities, textures and all other artifacts such as reflection to obtain those pixel values and paint it on a scene for which the camera angle is not available or the camera shots are not available. So, that is very interestingly image based rendering for you. The images produced by IBR systems are often more realistic when compared with classical rendering models. The basic principle is to take some subset of the required viewpoints. What are these concept of these viewpoints, which I just talked about this viewpoint right now. As you see the lecture right now in front of me, there is a camera which is recording my lecture. So, that is a viewpoint. So, that is a viewpoint, and of course, you can have another viewpoint where the camera is shooting from the side. So, these are two viewpoints, and you would like to generate a third viewpoint and simulate it. Okay. So, the basic principle is to take some subset of the required viewpoints, and from these synthesize the picture that we need to see from a new viewpoint. So, that is image based rendering for you. Well, there are many methods of image based rendering available in literature, and you can have hours of lectures of these concepts mixed with digital image processing, which will be covered in the next two slides. There are concepts based on image simulation. There are concepts based on the method of animation which we talked about, the motion capture, which are used for image based rendering. We will discuss just two of the common methods on image based rendering methods, and the two methods are, one is called mosaicing, which is also basically an area covering under image processing, where we match multiple images by aligning and pasting images to have a wider field of view image. Well, that is more of image processing than image based rendering, but that also could be used, and also the concept will introduce this terminology of light field rendering, or what is called as lumigraph, where the light field rendering is the process of rendering novel views of a scene captured by the light field function. Well, this light field rendering lumigraph is a concept where you define the light rays. It is an extension of light ray tracing. If you remember light ray tracing in shading method, where the light rays are coming out from the center of the COP through the image pixels and moving towards the objects. Well, you can define light rays like that. In case of light field rendering or lumigraph, we talk about a 4D vector defining my light source. You can visualize as if you have a point u1 v1 at the near plane and a point u2 v2 at the far plane, and there is a vector which connects these two to simulate your light ray, and that is what you vary to simulate the effect of light field rendering. So, these are the two methods we commonly used, but there are other methods used in image based rendering also. Let us look at mosaicing for an example. If you have these two images, you can almost see for yourself that they are the images taken at the same location, but at two different viewpoints. Well, the camera has moved itself or it has rotated by itself, and there are certain sections on the left hand side of the picture on the here which is absent, and there are of course certain parts on the right hand side picture which are absent on the left hand side. But you can see there is a small section here which is common. The right part of this image of the left image is common to the left part of the right image here. As you can see, the front end of the bus with its right window here and the corresponding temple like structure here is common. So, you can use them to match and simulate and create a larger panoramic mosaic image like this. Okay, that is possible. As you can see that there will be some parts of this image which will not be available, but as you can see now it shows that not only that the camera has moved and shot the right frame from left to right as it moved, but it also rotated and turned by itself. We have a shift in the pan and the azimuth angle as well. It has probably gone through a pan azimuth scroll, and what has been done is you find out the part of the image which is extra appearing on the right hand side of the left picture and merge it with that. So, you need to match some parts of this picture and create mosaic. So, this is an example of two frames to create a larger view. Okay. People have experimented with software toolkits available where you can take snapshots around you at full 360-degree rotation. Now, you can take snapshot about say 15 degrees or 30 degrees intervals, provided there is of course a little bit of overlap between two successive frames. Okay. As you say, if you are moving to the right part of the first frame should have some common part with the left portion of the second frame and so on, because you need to match and find out where you have moved, how much you have moved, and there are many good matching techniques used in image based rendering or mosaicing in this particular case to find out the alignment. It is basically called a concept of image registration. You use concepts such as image registration to find out the part of the pictures match with certain parts there and then align it and then create the larger mosaic, and you can actually create a 360-degree mosaic full around you, either in an outdoor or an indoor of a scene, but of course it takes a lot of computational time. So, that is mosaicing for you, and the two top images are mosaic together to form a panoramic view of the scene. Lumograph, we talk of a light field which is a 4D function, we just described it some time back, which describes the radiation across a boundary between the volume containing a scene and the disjoint volume in which the eye point may be placed. Okay. So, we come to the last concluding slide of this lecture, which talks about visual realism. Why are we talking of all these advanced concepts in computer graphics? Well, you can have a full-fledged course on advances on computer graphics where we just introduce some of these materials, and there can be extensive discussions on each of these topics and some which we have also not discussed, say procedural mapping, procedural noise creation, Perlin noise models, mode on soft modeling, video, image and video based rendering, creating shadows, reflections, all that. So, let us list some of these topics which comes under the falls of advances in computer graphics or virtual reality. And why are all these necessary? Because you need to create visual realism. Why do you need visual realism? Well, you need to create pictures. We talked of this at the beginning of the course somewhere, where pictures should be made almost real life or real life like, as close as possible, so that the better designer you are, better algorithm designer you are, somebody should not be able to distinguish between a real life picture and a computer graphics simulated picture. So, you need to bring in concepts of advances in computer graphics, virtual reality to simulate or to emulate visual realism in your pictures, and that is the objective of visual realism. The objective is to creation of realistic pictures. We will just go through a list of few concepts which are used. Techniques which are used to create visual realism is the effect of texture. We have seen a small example today. We talk about material properties on object surfaces. There is a concept of using shadows, procedural texture and noise. We need to create transparency in objects, because not all objects are opaque, reflection on object parts, shiny surfaces are necessary. It probably goes with material properties and object properties. The reflection goes with material surface properties, transparency will go with object material properties inside an object. We talk of also we need concepts such as radiosity and photon mapping. stereopsis to simulate the view of the human being or animals, where we use two eyes to see a view and observe depth rather than a single eye. Dynamics for animation, real life dynamics. Antialiasing we covered today. Improved displays, methods by which improved displays not only CRT monitors, but improved projection screens and projectors are necessary. Haptics, non-visual feedback and use of other senses, where not only visual feedback, but you need to transmit say pressure. Well, you can use audio and video together to make it real life mode, but in some cases for training use haptic devices where people can interact with the system in like a physical world. Suppose you are playing a game for tennis, and then when you hit a ball by moving your hand, well, the hand is covered by a glove which will give the effect of the impact of the ball. And you could be playing with a computer, or your partner could be also playing on the other side of the computer, and both will have haptic devices on. Haptic devices are in virtual reality are in great demand, and there is a lot of research which is going on in this field, and people use this for training pilots, for training in the army, also in defense, for various civil and commercial applications. Haptic devices are used. Okay. And of course, we talked a little bit about image and video based rendering. So, a combination of a few of these concepts or all of these will definitely help you to make your picture appear as real as possible, and that is the main goal of visual realism in computer graphics or virtual reality, where you want to create as real life simulation pictures as possible. So, with that we come to the end of the lectures on advanced concepts in computer graphics. Thank you very much.